Now we'll look at unsaturated hydrocarbons. So we saw before that saturated hydrocarbons had all single bonds. So then unsaturated hydrocarbons is any hydrocarbon that contains any sort of multiple bonding. So this would be, this could be looking at single or double bonds, triple bonds, all sorts of double bonds around the place, anything like that. Whenever the carbon and carbon, when there are carbon atoms that are not single bonded, that molecule is unsaturated. It's still a hydrocarbon, so it's still only hydrogen and carbon in the molecule, but there's just a little bit of flavor to how the carbon atoms are linked together. There are two primary types of unsaturated hydrocarbons, alkenes and alkynes. So still very similar name to alkanes, but you can see the idea is all in the naming of organic compounds, it's on the ending, right? So alk, basically that ALK just means hydrocarbon. And then there was alkanes, alkenes. And so ene, whenever we see that, that is the simplest alkene. It means double bond in the molecule. And alkyne, whenever we see that YNE, that means there's a triple bond in the molecule. And so here is your simplest alkene would be two carbon atoms bonded together. You cannot have a one carbon atom alkene because you have to have a double bond, so you have to have two atoms. Similar with alkane or alkynes, it could be two carbon atoms triple bonded together. So you'll note that one of the things I do want to note is that when we're talking about naming, we're not going to go too hard into naming, just kind of want to recognize kind of some of the general patterns, ane, ene, eind kind of ideas. But you'll note that even here, like acetylene, that's definitely triple bonded. This is an alkyne. There are a lot of historical names for molecules, especially smaller organic molecules that don't follow the rules. That's one of the reasons why we're not going to go too deep into this. But just want to be mindful that when we see this is still an alkyne, as even noted right here, just that the name acetylene would imply that it is a double bond. But instead, it's a triple bond. It is an alkyne. And we really do want to focus on the bonding determining the properties, not just kind of some historic name. Participation 428, question 3. Give the molecular formulas of the following hydrocarbons, A and B. This is the third question on participation 428 due Tuesday, April 28th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the document where these videos are posted. Again, give the molecular formulas of the following hydrocarbons. I got hydrocarbon A and hydrocarbon B. I want both of their molecular formulas. So, one of the things that's unique and special about unsaturated hydrocarbons is the fact that now you can bond with the carbon atoms. So this is unique and different from alkanes. So we're only going to talk about alkenes, but a lot of what we're talking about also applies and there's similar things going on with alkynes when there's triple bonds involved. We're just going to look, though, at double bonds. And basically, the general idea is the unsaturated designation, right? This word unsaturated implies that there's kind of some extra bonding going on between these carbon atoms. And you could change it such that those carbon atoms start to bond to other things. You know, it could just be something like hydrogen. You know, you could go to a saturated hydrocarbon. And we call these addition reactions. You are adding something into the molecule, right? You are adding something to attach onto where the double bond was in the molecule. Generally, these reactions are pretty spontaneous. Double bonds do tend to be reactive, but they can be kind of tricky to perform. You need special conditions, you need other molecules to perform. So this kind of general designation, what this tells you is that it's tricky kinetics, right? If you require special conditions or other molecules is just a fancy way to say catalysts. So you need a catalyst in there because these are tricky kinetics to occur. It's a very spontaneous process. You know, the thermodynamics tells us that this really should happen. It's just hard to sometimes make it happen. So addition reactions is the overall kind of type of process that these double bonds can do. But there's a lot of different flavors, a lot of different ways, things you can add on to the molecule. So for example, you could react it with an acid, you could react it with just water, you could react it with bromine, and you could react it with hydrogen. So you can do all sorts of react with different things, and you'll note that in general, what happens is in your reactant, you have, a carbon-carbon double bond, and in all of the cases in the product, that double bond is broken, and you're attached onto something else. There is now other functionality in the molecule. And one of the ways we can think about it is you can start to change the properties of the molecules. Chlorine, OH, those are polar. Bromine, you've got these bromines hanging on right there. Those are going to be potentially quite reactive. And so what you can start to do is you can modify, you can decorate your kind of hydrocarbon chain and get some sort of reactivity, get some sort of functionality, change the functional groups on the chain in the molecule. You can also just get an alkane if you want. And so these addition reactions follow a consistent pattern that's centered around just changing the double bond. So you'll note here I have a bunch of different alkenes. You can see I have different double hydrocarbons, just line drawings of hydrocarbons with double bonds in there. And I reacted with bromine, 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 and bromine. And every single time the bromine attaches where the double bond was. And so this is why we define what we call functional groups. The double bond in an alkene is the functional group. The double bond in the alkene is the part of the molecule that does the reaction. You'll note the rest of the molecule doesn't change at all, right? If you look in the bottom, there's all these other carbon atoms on the other side of the ring. They're all still there, and they haven't changed at all. The only thing you've changed is the carbons that were in the double bond. They're now bonded to bromine. And you'll note that every single one of these double bonds follows the same functionality, follows the same process. Each carbon atom is now bonded to bromine. So this is why we define functional groups. This is why we define these ideas of focusing on the double bonds, because there are certain reactivity patterns. This is the sort of fine kind of chemical changes and fine control we're looking at doing in organic chemistry. Overall, this molecule and this molecule is roughly the same, right? You have 3 carbon atoms. 1, 2, 3. 1, 2, 3. You have 3 carbon atoms bonded together. It's just kind of changing the decorations or changing kind of what it looks like. Is it double bonded or are there bromines hanging off the side? But you haven't changed the skeleton. You haven't changed the bones of the molecule. One very important application of these idea of addition reactions, or the reactivity of these double bonds, is that you can have 2 molecules that are both alkenes react with each other. And so what can happen is, you have, say, a carbon-carbon double bond right here, carbon-carbon double bond right here. All of these could undergo addition reactions. What happens is they can undergo addition reactions together to form what's called a polymer. A polymer is just where you have a bunch of, say, small molecules that have all been bonded together and linked in together. And these can grow up to molecules that have thousands of carbon atoms. And so one of the things we can do is really build these really long chains of molecules that have consistent behavior and consistent properties, because it's basically the same repeating unit over and over again that goes together to form it. And so these are 3 examples of alkenes. So ethylene is a simple one where we have just, say, the carbon-carbon double bond. And what you can imagine you do is you take one of these bonds from the double bond and you break it, and then you form a bond out to here to 1 carbon atom and a bond out to here, right? That's right here and right here. You're forming those bonds. And so you can make what's called polyethylene. That is like plastic bags. So, disposable plastic bags, that's made from polyethylene. Vinyl chloride, where you have, say, a carbon-carbon double bond onto a chlorine. Oh yeah, ethylene, over 160 million tons of ethylene are used every year to make polyethylene. So this is one of the biggest organic, industrial organic chemistry applications. Vinyl chloride, where you have a carbon-carbon double bonded to a chlorine. Those can link together, and you make polyvinyl chloride, or, shortening of it, PVC. C. So PVC piping is an organic compound as well that has different properties. The chlorines overall, this is a very similar molecule. It's just a really long chain of carbon atoms, but you have some chlorines hanging off the side. It makes it a little more polar. And so that changes the properties. You can get a little bit stronger, a little more resilient. And so you can get a lot of different properties. One of the things that's nice about all of these is you'll note that all of these are basically just giant alkanes. That makes them very nonpolar, makes them very insoluble in water. That's why we can use polyethylene bags to say hold wet things, and we can use polyvinyl chloride piping to say carry water, right? It would be bad. You wouldn't want to use material that would say dissolve in water as you're piping. That'd be a problem. And so these are really easy to work with. These plastics are relatively easy to work with, really very wide applications, very lightweight, very cheap. Styrene, again, the carbon-carbon double bond is up here. You form links between those. Now you have this kind of big ring hanging off the side. Polystyrene is also known as styrofoam, which is a brand name. Polystyrene is the molecule, styrofoam is a brand name. And so again, these polymers that you produce that all are based around reactivity of unsaturated carbon or unsaturated alkenes is a huge part of industrial chemistry and something you have interacted with every day of your life. Plastic is just a huge part of what you're doing. The computer you're watching this on is maybe made of plastic or has plastic casing. Your phone has plastic in it if you have a phone case, if you're watching on that. A mouse that you use, there's just plastic all over the place. And it all comes from controlling the reactivity of double bonds and knowing that you can get them to behave in consistent ways and they will just keep linking together, making really big molecules. So when we're starting to look at hydrocarbons and thinking about what hydrocarbons do, they really kind of serve as the backbone for organic molecules. Carbons that are single bonded to each other are not reactive at all. When you start to get some double bonds, some triple bonds in there, you start to throw in some reactivity, but still hydrocarbons in general are kind of the backbone. They're the structure of the molecule that you decorate with functional groups. And those functional groups give some properties to the molecule. So this molecule over here is erythromycin. This is an antibiotic. You can see there's lots of lines. Those are all, again, carbon atoms that are linked together. There would be hydrogens hanging off of those. And then there's O's, N's, and some H's that are attached to the O's are also written in there for the different functional groups that are in this molecule. You'll note there are some dashes and wedges. Those just indicate 3D structures. The dashes, this is going away from you. This is coming out towards you. So it's just implying the three-dimensional shape. Erythromycin is a molecule with a very particular three-dimensional shape that is necessary for it to be an antibiotic. So we can see there's a lot of carbon and hydrogen, kind of carbon backbone, hydrocarbon skeleton, if you will, that is linked, that has a lot of oxygens kind of decorating it. And so what we want to do is kind of think about, what affects, what properties do those oxygens impart as we start to look at other functional groups. But importantly, the backbone, the skeleton, the actual kind of structure of the molecule, all these linkages in here are held together by hydrocarbon portions of the molecule. All right. 3 questions on participation 428, including one in this video. You want to find all 3 of those questions, get them answered, and get those answers submitted over on Blackboard by Tuesday night. Wednesday, we have the midweek homework due over on Active, and Wednesday in our on-campus time at 11 a.m., we'll start with the Chapter 21 participation quiz. It's all about nuclear chemistry. That'll be in the classroom, 141. And then we'll go over to the lab room afterwards, and we'll do the lab practical starting at 11:20. There are questions. There's on the main page of Blackboard at the top, there is a folder with some